All right, hello everybody, and welcome to day 4 of Sequestration Week. Today we're going to be talking about green concrete. Concrete, one of the most important materials in the history of mankind, and a big source of carbon at the moment. But we have some really exciting news to share, and 3 great presenters who are going to dive into this that we'll be introducing in a moment. My name is Brian Stewart from Electrify Now, and my colleague Joe Wachunas and I will be moderating today and helping to just move things along, but most of it's going to be from our 3 presenters. Thank you for tuning in. I just want to give a little bit of background about Electrify Now. If you're unfamiliar with us, we're a voluntary organization based here in Portland, and our mission is to help empower everyone to help create the clean energy future that all of us want and need. Along the way, you will be able to learn how to reduce a huge portion of your carbon footprint by taking these 3 steps that we ask people to think about in their own lives, which is about getting clean energy into their homes with renewable electric supply. It's very possible to do and affordable almost everywhere in the United States today. And then look around your home and just take note of all the devices that we all own that burn fossil fuels, and every one of those can be replaced with a clean burning electric option powered by renewable energy, which will create 0 emissions. And those devices actually perform better than their gas counterparts and can save you some money in terms of operating expenses. And then finally, transportation is the other big one where electrification is really accelerating. There's some fantastic options with EVs that are on the market today and new ones coming all the time. And then finally, we realize that this transition only works if all of us can take part in it. And when you're talking about voluntary action, there's some people who are in the low income or communities of color, BIPOC community, who might be in danger of being left behind with this transition unless we create policies to make sure that those folks transition along with the rest of us. So that's what we call Electrify Everyone, and we have some tips for people on all of these that you will be able to find out more information about on our website, and you'll be able to see how a typical family could avoid 20 tons of carbon emissions per year by taking these steps. We have tips, trusted resources, even some discounts that are available here in the Northwest with suppliers that we know and trust. So check it out on electrifynow.net. I also want to give a huge thank you to everyone who made a donation. We ask for voluntary donations if possible as a kind of way for us to raise money for local charities. In this case, we're raising money for Friends of Trees, a local organization here that plants trees, mostly in the Portland area, helping to create a great canopy for our city to make it more livable, lower the temperature, and obviously absorb a bunch of carbon, and provide some great opportunities, learning experiences for children and others in the community. So thank you for your donations. We're really happy to be able to pass it on to Friends of Trees. All right, Joe, so why are we talking about carbon sequestration?
Hey, well, welcome back, everyone. If you've joined us for other 3 events so far in Sequestration Week, we are doing an entire week devoted to sequestering carbon, pulling it out of the atmosphere, which is a new take for us. We're usually talking about how to reduce emissions, and we feel like the clearest path to do that is through clean electricity. But this week, we're taking a moment to talk about how to sequester carbon, because there's going to be some industries that are difficult to reduce their emissions and to electrify. And also, scientists are telling us that we're still going to need to sequester some of the carbon we've been emitting over the past couple hundred years into the atmosphere. So, for example, today we'll be talking about concrete, which is around 8% of our emissions, and Michael will be confirming that stat in just a second. We need to, there are some possible ways to sequester carbon within concrete or sequester carbon that is being emitted by concrete. And so we want to be talking about these really important discussion points. So that is the impetus behind Sequestration Week. And if you've missed any of our webinars, I'll put a link to our YouTube channel. We've been recording and posting them all really quickly on our YouTube channel. We did carbon capture and storage on Monday, forests Tuesday, grasslands yesterday. Today's on concrete, and tomorrow we'll be finishing the week with a great conversation on soils. So please join us for that as well. And real quick, a housekeeping thing, please put any questions you have either in the chat or in the Q&A. We'll get to as many as possible during the Q&A portion of our webinar.
Great. Well, I'm really excited about the panelists we have today, our presenters. We've got two ready-mix suppliers who are pushing the envelope in terms of the technology around concrete. We have Michael Bernert, who's the Vice President of Wilsonville Concrete Products here, a local operation, and it's a family-run business that's, again, like I say, really experimenting with new ways of creating concrete and delivering it to consumers so that we can reduce carbon emissions. We also have Alana Guzzetta from US Concrete. She's the National Research Laboratory Manager. So she's working up front, working on new ways to make concrete. And again, a lot of this work is in service of reducing the carbon impact of this product. So two great suppliers. And then we have Alex Boetzel, who's Director of Operations at Greenhammer, also here in Portland. And they are a builder with doing LEED certified buildings and other green building techniques to lower energy consumption, increase efficiency, and lower the kind of embodied carbon in the buildings that they produce. So I think we've got a good spectrum of speakers here who are looking at things from slightly different angles, but are going to be able to give us a really great picture of what concrete looks like today and where it is going in the future. So with that, I'm going to turn it over to Michael.
Well, Michael's getting going, folks. One thing I did forget to say was if you feel comfortable and want to say where you're tuning in from tonight, we always like to hear where people are tuning in from. So go ahead and put it in the chat.
Thanks, Brian. So thank you, and thanks. Apologies for the time there getting set up. So I'm the 5th generation of my family that's been a part of our business. We got started in the 1880s in the tugboat business. In the 1950s, we started producing concrete. They were the largest independently owned producer of concrete in the markets we serve, which is mostly focused in Western Oregon. Concrete is the most common building material in the world. So it's second only to water in terms of human use, and it's everywhere. It's in our roads, our homes, our bridges. It is what supports our skyscrapers and our stadiums. And it's a versatile, strong, low cost, and long service life material. Because of those advantages, it's ubiquitous, and it's hard to explain the scale, the immensity of the amount of concrete that we use globally. The easiest way for me to think about it is a typical residential driveway. So this is the average American driveway. It's about 640 square feet, and it's a 4-inch thick slab. Every day, globally, we produce enough concrete to pour about 9.5 million of those driveways. That's enough concrete to cover the entire city of Portland, all of the offices, sidewalks, and roads, but also all of the residential neighborhoods, the trees, the parks, the green space, in 4 inches thick of concrete. It's truly a mind-boggling amount. That's the amount poured in just a single day. Globally, over a year, there's enough concrete poured to cover the entire nation of the United Kingdom. So I can just rattle off example after example, but it's a massive quantity of physical material. Given that scale, it's no wonder that has a dramatic impact on our planet. About 70% of the carbon footprint from concrete is coming from a single ingredient, which is cement. Cement is the binder that holds concrete together and allows it to gain strength over time. The manufacturing of cement alone accounts for somewhere between 7 to 8% of global human-caused carbon emissions. So it's a huge part of the climate crisis, and that's why our producer community and other folks in the industry have a real need to take dramatic action quickly to reduce that footprint, and also look for opportunities to transition the built environment into a source of sequestration instead of being a source of emissions. We're going to talk a little bit about sequestration later, and I think Alana is going to touch on that. For now, I'm going to focus a little bit on the opportunities to reduce current emissions using existing technology. Through existing technologies that are off the shelf today, there's the potential to reduce emissions by about 50%. So there is some real promise in terms of tackling that 7 to 8% equation in the near term. And there's also real opportunities in the long term to pursue some of these sequestration technologies. Before we jump into the technology, I did want to do a brief introduction on cement chemistry, and it helps educate why cement has such a high carbon footprint. And I have a disclaimer that this is a massively simplified explanation, and so I apologize in advance to any engineers or chemists who may be participating. But at the simplest level, cement is made from limestone or calcium carbonate. That limestone is heated up in a cement kiln to over 2,500 degrees Fahrenheit. Most of that heat comes from the burning of fossil fuels today. And as we know, that's a significant source of carbon emission. The heat creates a chemical reaction, which produces cement on one hand, but in order for that chemical equation to balance, it also creates what we call process carbon, even more CO2 pollution. So the reason why cement has such an outsized impact is because of the burning of fossil fuels on one hand, but it's also coupled with the industrial process itself is a source of additional carbon emissions. As we look as an industry on how we can tackle that problem, we have to pursue an all of the above approach, where we are attacking emissions and looking for sequestration opportunities throughout the life cycle of concrete. Alex and his team at Green Hammer are experts in constructing structures and placing them in service in such a way as to reduce their carbon footprint. I think he's going to speak in his presentation about that area of the life cycle. There are opportunities through recycling buildings when they're being decommissioned to turn that concrete into new material to reduce demand. And so we can recycle that concrete, turn it into new aggregates. One of the opportunities that Alana is going to speak to is Blue Planet. Blue Planet is a technology where carbon dioxide is used to make synthetic aggregates, and then those synthetic aggregates are placed into the concrete, and that's a true sequestration opportunity, which permanently sequesters carbon dioxide into our built environment. Alana's also going to speak to Carbon Cure. Carbon Cure is an opportunity and a technology to inject carbon dioxide into the concrete batching process, and again, permanently sequester that carbon dioxide into the built environment. Carbon Cure and the Blue Planet technologies are emerging and reaching commercial scale. In the meantime, there are things we can do today to significantly decrease the cement that's in our concrete mixtures. So taking cement out of concrete is one of our biggest opportunities to reduce emissions today. In our company, we launched a product line that's called Rocks Concrete, and it uses what are called supplemental cementitious materials in addition to a very specific type of cement called a type 1L cement to take cement out and replace it with the supplemental cementitious materials. We currently have two products that we sell. One is called Steel Rocks, which uses a byproduct of the steel manufacturing process as the primary SCM, and it reduces the cement content by about 50%. And I think Green Hammer uses this product in a number of their recent structures. We're also starting field trials this year with a product that we're calling Clean Rocks, which reduces the cement content by 75%. And it uses a slightly different technology called alkali activation in order to help those SCMs gain strength at such a high level of substitution. Both of these products and our entire rocks concrete offering is carbon neutral. This was a challenging decision for us to make in terms of, are we just paying to pollute? And so I'd welcome a discussion during Q&A about how to think about carbon offsets and how we came to the conclusion that it was the right decision. But that is a part of where we're moving our company in terms of purchasing those offsets currently. So my email is up there in case anyone wants to follow up afterwards, and I'll turn it over to Alana to let her share about the technologies that she's working on at US Concrete.
Thanks, Michael. Maybe while Alana's teeing up, one question for you. With your products, the Steel Rocks and Clean Rocks, the 50%, 75% reduction in cement, does it roughly correlate that the CO2 emissions would roughly be half and roughly 3/4 less by making that move?
Brian, we're not quite there. So compared to the market average right now, our Steel Rocks lineup is about 30% below the other products in the market in terms of carbon footprint. Our SCMs do have some carbon footprint. So the carbon footprint associated with our slag product is about 1/10 of the carbon footprint associated with traditional cement. So today we're at 30% reduction. We think we'll be at about 50% reduction within the next year. And with the technologies that we're using, we can get to, you know, probably 50 to 60. Once we get past that, we're going to need to be looking at some different technologies. And just as a reminder for the chat, an SCM is a supplemental cementitious material.
All right, thank you.
All right, cool. Well, thank you, Michael. I'll go ahead and jump into my portion now. Great to see everyone. Thanks for those of you who are sharing where you're from. I'm based out of San Jose, California, so it's fun to see the California support, and then really awesome to see the whole variety of where everyone else is coming from. So thanks for joining today. So I'm going to start with talking about an environmental product declaration, because that has a metric for measuring the sustainability of concrete, and some of my examples in show reductions are based off of that metric. So I just want to, I'll start with an introduction on that, and then I'll be going through some of the different, all the different technologies that are available to concrete ready mix producers today that can have very measurable impacts that Michael really introduced and touched on in his portion. And then I'll go into just a little bit on specifications, because that's an important part of being able to implement low carbon concrete, and touch on recycled concrete aggregate before handing it off to Alex. So an environmental product declaration, usually abbreviated as EPD, is something that basically looks like a nutrition label, and it has a variety of metrics that give quantifiable measurements for the sustainability or the embodied carbon of a concrete mix. And the one that's most commonly looked at is the one that's highlighted in red at the top, which is called global warming potential. And often this is called a GWP. And so in the example on the screen, the GWP of this mix is 435. That's specific to the mix design batched at a specific plant. So as a ready mix producer, we have operations in different parts of the country, but say specifically in the San Francisco Bay Area, we have 19 different plants. And so what this is take into account are all the raw ingredients that are in the mix and what it took to transport them to the plant where the concrete is going to be mixed at. So that's how an EPD is going to be specific to a mix design that's batched at a specific plant. And concrete was actually the first building material in North America to have an EPD. And now there are a variety of different products that have EPDs available. So what I show on the screen is just a mix design, what you might be familiar with looking at if you deal with concrete mix submittals, or if you're a purchaser of concrete. This is what you're going to see as the proportions for all those ingredients coming into place. And so that EPD is taking into account what was the processing emissions for each of these ingredients, what was the emissions attributed to the transportation of these ingredients to the concrete ready mix producer plant, and then what energy and emissions go into mixing all together and producing the concrete at the supplier's plant. And so I'll be referencing this page to go through what the impact and the ability to lower the embodied carbon of the mix is for each of these ingredients. Looking at the mix overall, this is a breakdown of the GWP for 3 different mixes. And looking at where is the majority of that embodied carbon coming from. As Michael said in his presentation, it could be about 70% comes from cement. And so in this specific breakdown, we took a look at 3 different mixes. The dark gray bars are a 100% cement mix. So that means the only powder in the mix is Portland cement. And then the red bars are for a 15% fly ash mix. So that means 15% of the cement is replaced with different powder that we call fly ash. That's a byproduct of burning coal, and it's a waste product that would otherwise be put into a landfill. And then the light gray bars are from a 50% cement replacement mix, where we're using a blend of supplementary cementitious materials that Michael talked about. And so you'll see that with the 100% cement mix, where cement is your only powder, in this specific mix example, 90% of the GWP for that mix design comes from the cement. And then you can see as you start replacing that cement, it becomes lower. And so you're anywhere from about 70 to 90% of the embodied carbon in the mix is coming from the cement. And so if we take then a first look at cement, what are our options then for reducing the embodied carbon of the mix? And one thing is looking at the type of cement that you're using. And so Michael talked about this, that they are currently using a type 1L cement. And what that means is it's coming from a different ASTM standard. A lot of the cement that's more common that we're used to is an ASTM C150 cement. Different parts of the country will use different types. Specifically in California, we're using a type 5 cement. And so that's one where the chemistry is such so that it can be more resistant to sulfate attack. And if you have a cement that meets C150, it can contain a 5% limestone. And so that limestone is talking about limestone that has not gone through the kiln and is blended in with the cement product that has been processed through a kiln. But a C595 cement is a blended cement, and so that allows for a higher amount of limestone. So you can get up to 15%. Commonly, we see cements having 13 to 14% limestone. And so what this does is it reduces the embodied carbon of your mix by about 7 to 8%. If you're taking a C150 cement and pound for pound replacing it with a C595 cement, that's going to result in about a 7% reduction in your GWP for the mix. In California, Caltrans is currently doing a study on the type 1L cement, and once they approve the use of it, this is probably going to be a very common cement that you see used in California. So one way, if you're a designer, for specifications, allowing both a C150 and a C595 cement would allow for this lower embodied carbon type of cement. And for those in California, would be in preparation for the transition that's likely to take place in the next year or two. So then moving next into the mix design, the supplementary cementitious materials, these can be a variety of products. They're just different powders that can replace the cement in the mix. And we'll go through some of the options there. But first, understanding, going back to that chemistry equation that Michael was talking about, the calcium silicates are coming from your cement and they're mixing with water. And that chemical reaction is called hydration. And what you get as a result of that is something that we call CSH, calcium silicate hydrate, which is going to be that strong paste product that's holding everything together. It's holding the rock and the sand and all the powders. And that chemical reaction is what makes it go from a liquid state to a hard concrete and build strength and the density of that material. A byproduct of that reaction that's also mixed in with that paste is free lime or calcium hydroxide. And the benefit of supplementary cementitious materials is that some will have a little bit of reactivity with water on their own, but the majority of what they're doing is they're reacting with that calcium hydroxide, that weaker product. They're reacting with that and water to form more of that CSH, or that strong part of the paste. And so what that's doing is going to increase the strength of your concrete and also make it more dense as well. And so in an example of how the embodied carbon can be reduced with these types of products, this is an example where we've got 100% cement mix that achieves 6,000 PSI at 28 days. In this particular one, it has a GWP of just over 600. And then when we took a 50% cement replacement mix that achieved the same strength, you can see there's a 45% reduction in the GWP. And then with a 70% replacement of cement at the same strength, we were able to achieve a 60% reduction. And these are mixes that we're able to use out on the market in the San Francisco Bay Area, also in our East Coast operations as well, that we're able to use today. And then what this is an example of is showing some field compressive strength examples where we've got in the gray bar, that's a mix with a higher GWP. It's 15% cement replacement, compared to the red bars, which is a 45% cement replacement mix and has a lower GWP. And with this, you're seeing that we don't have to sacrifice performance of the material in order to have this lower embodied carbon concrete. And so supplementary cementitious materials very commonly today are fly ash and slag. Slag is a byproduct of the steel manufacturing, as Michael mentioned. And one new one that's available on the market now is glass pozzolan, which has a new ASTM standard specifically for it that just came out, I think it was about last year, maybe 18 months ago. And so the only glass pozzolan source that I'm aware of right now is in the New York area. It's something we've used in the lab for the last 5 years or so. And in New York, we've used it successfully on several projects and used it in combinations with other supplementary cementitious materials. So then next piece is the aggregates, the rock and the sand in the mix. And so if you go to this chart, this takes a look at a volume breakdown. So typical unit measurement for concrete is cubic yard. And so if you divide up that cubic yard by all the different constituents that are in it, you're going to find that about 60 to 70% of volume is made up of your aggregates, your coarse and your fine together. And so while cement is a significant portion of the embodied carbon, the aggregate is a significant actual product in your concrete mix. And so it plays a very important role as well in lowering the embodied carbon and the form of your concrete. There are a variety of different aggregates available and a variety of different reasons you would choose them. You can have high strength aggregates or high performing aggregates, which means you're able to achieve higher strength concrete, lower shrinkage, which is important for as a piece of helping to mitigate cracking potential. And then also have a higher modulus of elasticity or a higher stiffness of the concrete. Your kind of typical standard gravel aggregates, local to our area, we're going to be achieving 3,000 to 5,000 PSI concrete with that and going to the higher strength aggregates for anything above. There are also lightweight aggregates available for reducing the weight of a structure, reducing the weight of the concrete. There are different options available. A natural lightweight, which would be something like a pumice or a scoria, is going to have a lower embodied carbon than a manufactured lightweight. Manufactured lightweights are going to be things like expanded shale, expanded clay, and those are manufactured by going through a kiln process. So that's what gives them a higher embodied carbon. And what you have available in different markets is going to vary on your location and sources that you've got available close by. But those are things that conversations you can have with a ready mix supplier. A specific type of high performance aggregate is Orca. This is a US concrete aggregate that we have out of British Columbia, Vancouver. And this is an example of what we're able to do with that. So we're able to get cement efficiencies with this type of aggregate, and better efficiencies means that we can lower how much cement is in the mix. And if you recall from previously, the cement has the highest embodied carbon in the mix. So being able to lower how much cement content you need in the mix is going to further reduce the embodied carbon of your mix. And so for the example that you see here are 3 different types of mixes. And we've got one example with our Orca aggregate for each one of those, which are the red bars. And then the black bars are a local kind of standard quality gravel. And what you can see is that we're measuring cementitious efficiency in terms of PSI per pound. And so we're above 10 PSI per pound by using the Orca aggregate. And we're within the 8 to 9 PSI per pound range, but with a different aggregate. And so with that, the Orca mixes are going to require less cement to achieve the same compressive strength. And so the next on the list are going to be admixtures. This technology has been developing over the decades, and a lot of these and some of these technologies have been around for a while and been very commonly used. With admixtures, you're also able to improve your cement efficiencies as well. So that PSI per pound, you can reduce the amount of water that's needed in a mix. And there are even newer admixtures that are on the market now that actually help to give a strength boost. And so that's another way to be able to achieve the strength that you're looking for and do it with less cement in the mix. And so then, as Michael mentioned, carbon cure is kind of the newest technology or the newest ingredient that we have to work with in ready mix concrete. Carbon cure is a technology that injects recycled CO2 into the fresh concrete. This is the first technology available to inject concrete or inject CO2 into ready mix concrete. And so with this, we actually have this in both our San Francisco market as well as our Washington, DC market. And we've been using it for a couple of years. Great benefits to this are that it's not going to change the appearance of the concrete to contractor. So the workability, and everything that you see as a fresh property is going to stay the same. The way it works is when you inject the CO2 into the concrete mix, it turns into carbonic acid and reacts with calcium ions from the cement and forms very small size calcium carbonate. And so that's what Michael talked as limestone. So these very nano-sized limestone particles are going to help promote the hydration to react a little more early on and get at the right dosage, give a strength boost to the concrete. And with a strength boost, you have potential to further reduce the amount of cement that's in the mix. And so this is something that we've done successfully in both of our markets. Particularly, we have it available at 7 different plants in the San Francisco market. And so in 2019, we were actually able to do a mat slab delivering out of 6 different plants for over 7,600 yards in just under 11 hours. So we were producing that at a rate of 750 cubic yards an hour. The amount of sequestered CO2 is about 0.5 pound to 1 pound per cubic yard. And with this, we're able to look for opportunities as well to optimize the mix and further reduce the amount of cementitious material. And so then lastly, going into specifications, all of these things that we're able to do, if specifications are designed to be very prescriptive, then it's that can be a barrier to going as low carbon as you can go on a mixed design and still meet the performance. And what you see on the screen isn't intended to be read. It's all very tiny writing, but what it is a resource we have available that I'm happy to share with anyone who's interested, where it goes through kind of 3 key things that we see in specifications that tend to be very prescriptive for the mix. That can be a barrier to going low carbon. And so we describe what we believe the intentions are for those and how to still achieve that intended performance, but be more performance-based in the specification. And this just shows an example of water cement ratio. If that is limited at a pretty low number, lower than what's needed for the strength that's needed, you're actually pushing up what the embodied carbon is of the mix, and unnecessarily in a lot of cases. And so what this shows is 4 mix examples at a 0.45 water cement ratio. And when you look at those 4 mix examples at a 0.50 water cement ratio, you can see that there's about a 7 to 12% reduction in the embodied carbon of those mixes. And with recycled concrete aggregate that Michael mentioned, this is another benefit to concrete in that when there is a waste material or there is leftover product at the end, it doesn't necessarily have to go to a landfill. It can still be used in a variety of ways. And one of those ways is recycled concrete aggregate. And one of the challenges of this is managing the source. So you're going to get a little more variability in that type of aggregate. And so making sure that you're managing that to have predictable performance in concrete is important. But what this is concrete can be turned into recycled concrete aggregate, either as demolished concrete from a structure or as fresh concrete that gets returned that's left over from a project that can be laid out on the ground when it comes back to the yard, and then taken and crushed into an aggregate to be used in a new concrete mix later on. And this just shows the variability that you can get with recycled concrete aggregate. You can have some pieces that are going to have a high content. Some pieces are going to be loose aggregate that's loosened from the crushing process. And so just making sure that you're managing the source, as long as you're doing that well, that's something that can definitely be used into new concrete and used with a lot of good quality. With this also, concrete naturally, when it's hardened, will absorb CO2 from the atmosphere and produce a carbonation reaction. And so concrete itself is something that also sequesters CO2 from the air just naturally. And when you take it and crush it into an aggregate like this, that exposes more surface area and helps to also draw more CO2 out of the environment. And this is just kind of a summary that I'm happy to share with anyone that shows where different strategies that we've talked about today, what applications they work best. And kind of the importance of this slide is not even necessarily the specifics, because the specifics will vary depending on what market you're in and your ready mix producers, but how important communication is between the ready mix producer and the design team and the contractor to make sure that you can put together a mixed design that's going to be as low carbon as possible, but it's also going to achieve the structural properties that are needed by the designers, and then also accommodate the contractor's schedule and placement needs. And so with that, going into the contractor's piece, I want to hand it over to Alex.
All right. Well, thanks, Alana, and thanks, Michael. Let me cue up my slides here. Obviously, there was a lot of technical information, awesome information in there, and most people are going to feel like and want to review the slides afterwards to make sure they really catch all of the detail. But so the perspective that I bring to, as you can see, like we talked a lot about reducing the carbon footprint of concrete. And so as we're waiting essentially for a lot of the carbon sequestering opportunities to come out of the labs, I wanted to bring the perspective of our practice. So I'm with Greenhammer. We're a small design build firm in Portland, Oregon here. And to bring this in context of a little bit embodied carbon, I wanted to take a little bit of time to talk about operational carbon, which is really what most people have in the past looked towards reducing carbon emissions, right? So what we built is projects like these, small multifamily projects that are zero energy, which means that, here's a little definition. The projects produce as much energy as it uses over the course of the year, right? Really dramatically reducing operational carbon essentially to zero. So how do we do that? Just real quick, we build a high performance enclosure. We use high efficiency systems, and then on-site renewables, take care of the rest. In addition, right, we're looking at policies that local jurisdictions like the city of Portland, Multnomah County, where we have that, to decarbonize the grid, right? So pretty soon our operational carbon is going to go to zero. And this is where the embodied carbon of materials become more and more important, right? And initially we were thinking to focus on operational carbon, which we did, and we have huge successes. So this is really our next frontier in a practice like in ours. What that means is we were really interested in looking into how our buildings perform in terms of embodied carbon, right? So you can imagine that for zero energy projects, there's additional embodied carbon, right? That additional insulation materials like that, a PV solar array. And we were interested in this idea that we really are shooting for zero emissions at 2030, right? So obviously, a building like this is going to save energy over its lifetime, which might be 100 years or more. But what we discovered in this analysis is, one, that actually a zero energy building is going to show carbon savings after a year compared to a cold building, right? So that was encouraging that our additional effort that goes into creating a zero energy building doesn't take 10, 20 years to pay back, so to speak, in embodied carbon. But as we've been talking about, it's still concrete is our most carbon intensive product. So what I want to talk about is and maybe somebody else's practice, like how do we make that change? What are the implications in the field? And so what we're finding is important is that we have to find the right partners, right? If you talk to your concrete suppliers, you have to talk about your goals. You have to bring the supplier in the conversations like we just had. Michael and Alana talk about, because they can really inform the conversation. Ask for CSMs, this is like the term of the day, I guess, and ask for EPDs. So EPDs are important. EPDs are really, like Alana was saying, our nutrition label for materials and embodied carbon. And so please ask for those. There's other materials you can start asking for these. Not every industry has these available yet, but if we ask for it, we're going to get those more. One thing that's important, though, that I wanted to point out is if you talk to your concrete installers, there's an art and a craft behind installing concrete, right? So this might sound a little flippant, but changing the mix design of a concrete could, for some people might be equivalent to changing, the family recipe on a holiday dinner. They have like decades of experience with certain mixes, what they can do, how they perform, like where their strengths lay. So changing specifications is going to be important, but there will be hesitation, from the trade partners to change their practice. And so this is going to be a slow educational process, and it has to be collaborative to really change the industry to get these reductions that we can realize today. And the other aspects, the other way this impacts our concrete trade partner has to do with time, right? Some of these mixes perform a lot better over time, like Alana was illustrating so well just before. But there's also aspects, particularly for smaller projects and smaller concrete installers, that really matter. For example, form removal times, right? Some concretes might be stronger over time, but the initial strength, that you get over 24 hours or 48 hours is lower. which means they have to plan on, removing forms later. And concrete installers might rely on moving from one project to the other. And so if they have delays, that has to be factored in. The other one I think that's fairly important, and that's our experience, has to do with flat work, right? So the driveway that Michael was talking about, for concrete slabs and others, are a very specific installation, and those have to be protected, right? So we have it now that we're reducing cement, the behavior is different, and the installation process is different, and the finishing process is different. Again, those are things that that need to be discussed. We actually had basically samples that we placed with our trade partners to increase the confidence in the product. So those are changes that don't happen overnight, but they're important that we have those discussions right now, because like we were talking about, we have the opportunity to reduce the embodied carbon in concrete by 50% or more today, and it's not common practice yet, right? So we have to ask for it in order to change that industry. Again, we talked mostly about what's possible today in terms of reduction. This is the carbon sequestering week, and we touched on some of those opportunities. Again, the 50% reduction with cementitious alternatives compared to what we can do today with like a product like Carbon Cure, which, Alana, correct me, but I think we're around 5% reduction, or 5% of the emitted carbon can be sequestered. So those are still big gaps that we need to and want to bridge. But similar to the slide I showed in the beginning, we're reducing operational carbon and turning now to embedded carbon. The same can happen with, once we are reduced, like Michael was saying, the embodied carbon due to cement by 50, 70 or more %. Now, like, some of these technologies make real sense. And so this is really mostly what I had to say. Again, this is from the perspective from us and how to actually get to include these products. And I hope we could start, like our conversation around these alternatives. Some came up, Blue Planet in terms of aggregate, the alkali activated slag concrete. One product that I wanted to specifically point out here, that because it was new to me, and thanks for John Mead to point it out to me actually last week, a colleague here in Portland, is biochar, right? So a product that can also help sequester and strengthen. So the opportunity here is really to combine sequestration with an improved concrete product. So we'll stop sharing now, and hope we can have that conversation around those products. I don't know, Michael and Alana, you have those products in your laboratory. When do you see, like people like us, to be able to have access to those products and implement them in our products and our projects?
Yeah, from what I've seen in my experience, Blue Planet seems to be one that could be one of the closer ones. What's interesting about Blue Planet is that's taking CO2 and sequestering it onto an aggregate. And they have a couple different technologies. They can either coat an existing aggregate with calcium carbonate that's made from the CO2, or they can produce a brand new aggregate from scratch with all of that CO2. And like we talked about, aggregate is a really big volume within concrete. So that's where it's got really high potential to sequester a significant amount of CO2, potentially to the levels that bring it to zero or to negative. That's something that we've worked with in our lab with them, and that's an exciting one that's coming out.
On Monday we were talking about carbon capture and storage, and one of the scenarios that was discussed on Monday was cement making as a good application for that, because we know that cement's going to be needed for a long time in the future. You could argue that maybe we won't need it for our gas plants and coal plants. They're not putting them on coal plants because coal plants won't be around, but you could argue we won't need them for our energy supply, but some of these process carbon problems like steel and concrete might be a good application. So one of the things I was just wondering about is it feels like if you could combine, capturing flue gas to capture the process carbon and maybe even some of the heat that you were talking about, Michael, or the CO2 that's created from the heat that you need, these high temperatures. So you basically reduce the emissions to zero, and then you have on top of that some sequestration from either the carbon cure technology or these aggregate technologies. Then it feels like you've got more levers in order to not just reduce through some limited amount of sequestration, but maybe get to carbon negative. Am I understanding that correctly? Do you think that's feasible?
Yeah, I think if you have, we don't have cement production, so I don't have the expertise necessarily on running the cement plant of that. But if those emissions could be captured and utilized, which I think they can, my understanding is that there's a cost barrier there right now. If you're utilizing those and your cement is significantly reduced in embodied carbon, and now you're also sequestering embodied carbon, I think all of those adding together, that math works out to there.
And I would follow on saying that, I mean, how likely are we're in a race against time here for the climate crisis. And Michael and I were talking about an article, on some of the industries thinking by 2050, we'll maybe get to net zero. But, are we, with Alex's point that a lot of, concrete installers might be resistant to change, and how likely are we going to be to get to zero emission concrete? I guess I'll turn that to you, Michael. And is there a feasible path to get there quickly?
I think from a technology perspective, Joe, there is a feasible path. From a will perspective within the industry, I'm, as a producer myself, being in the industry, I'm scared, because I think sometimes our industry isn't forward looking and isn't being aggressive enough to pursue some of those opportunities.
That's interesting. I mean, one of the themes that's also come out this week is the kind of cost of carbon equation that could be a financial tool to help basically eliminate the added cost of getting to net zero or even sequester. So you can imagine maybe carbon offset programs that can fund this sort of thing, or just price tags on embodied carbon that become standard practice. But what do you guys think about that concept? I mean, I don't think there's any examples of that in the moment that are applied to cement and concrete, but is that being discussed, or do you think that's out there?
I think from a policy perspective, carbon needs to be priced, right? Until that happens, we're making economically irrational decisions. So, I think that's step one. And that's why I think it's important for the folks in the industry to step forward and purchase offsets, for at least some type of offset for the pollution they are causing. Until we price it, there isn't enough of an incentive to make the change.
Interesting. I'm looking at some questions in the chat, and this was new to me too when we were having some conversations before the webinar. That when you that hardened concrete will sequester carbon, and if you crush it, there'll be more surface area. Could you guys talk about? I mean, how much carbon are we talking that concrete, when crushed, or concrete just sitting there, can sequester? Is it a lot?
I don't have those specific numbers on me. There were Cal Portland produced a study that looked at quantifying that. I don't remember what their results are. I know also very recently MT produced a study and looked at it actually in terms of concrete pavements, because that's got a good amount of surface area. And I think their study showed that it was the actual quantity of it is a little lower than what some people had estimated at, but it's still an amount that makes a measurable difference, and I don't recall what those specific numbers are.
Another question from the chat is just to, and I know this would be a little bit tricky to answer, but can you give us just a rough idea about, like, if let's say I want to build a home and I insist that it's the best available low CO2 product, how much extra am I going to have to pay to get that? Can you give me a rough idea about what that looks like? I mean, percentages or something. What are we talking about here in terms of added cost?
Yeah, it shouldn't necessarily have to be extra in terms of going, what we can do with cement replacement now, going with equivalent strength. It's pretty equivalent pricing. Where you might run into higher cost challenges would be when you go really high cement replacement. You're going to have a slower setting time of the concrete and a slower rate of strength gain. Ultimately, it will get to a equal or better strength, but it's going to be a little slower. And so in projects where you're relying on higher strength, like Alex mentioned, for stripping formwork or for post tensioning or something like that, you're going to be sacrificing schedule a little bit if you're wanting to do those higher replacements, or in conditions where you have flat work. If you're using it for an application where a crew needs to be out there and put a finish on it, the longer set times could then cause the crew's going to have to be out there for longer, and so that'll be higher labor costs. You can mitigate that with accelerating admixtures, and so that's where there could be a higher cost component to the concrete mix to try to offset that set time. But you can really get low embodied carbon concrete for the same price if you're optimizing those different putting it in the right applications that will have a good impact and still maintain your stolen cost.
And maybe just one note, just to again, like to bring that home on the cost for the consumer versus the cost of the product, right? So we're really finding that the cost of the product is similar, but the cost of the consumer is, higher because of some of the restraints that Alana was talking about. And I just want to point it out, we live in this unfortunate world where we're in the middle of a boom, right? So if we ask our contractors and partners to do something different or new, they're going to be, they're going to think twice if they want to go the risk, right? Obviously, concrete going bad is a really difficult problem to remedy. So it's going to be a slow change, and I can't overemphasize that we need to ask for it, right? And we need to have that conversation.
I think I'm hearing you say, Alex, that they may that the concrete crew may charge you more, partly because of the risk, partly because of the unfamiliarity, right, and partly because this kind of resistance to change thing. That I get it. I mean, I understand that those people are on the hook if the concrete doesn't work out. So I can see that they're going to be a little bit reserved about making those adjustments. So, but it sounds like basically what you're saying is that the buyer, let's just say, is most likely going to pay more, and it's not necessarily because of the material cost, it's because of these other factors. Yeah,
exactly.
Question just came in on, we're at Electrify Now, we're tracking governments that are regulating natural gas or banning gas in new construction. Are we going to see this in the concrete industry? Have you guys seen jurisdictions regulating concrete, and do you expect to?
Norway. What's happening in Norway?
You don't have to go that far.
Alana was a part of an effort in Marin County, and she helped spearhead some of the jurisdictional regulations down there that now the city of Portland is actually following suit on. So I'll let her speak to some of her work with that.
Yeah, there was a team of people that worked with Marin County that we put together. It's kind of the first concrete code that incorporates not just the performance requirements, but also embodied carbon. And the way we set that up is that for different compressive strengths, there's a embodied carbon limit. And that limit can be regulated one of two different ways, either with a GWP or with a cement content limit. So there's a maximum cement content for each different strength and a maximum GWP for each one. And that allows that if a producer doesn't have EPDs, they're still able to meet the requirements by limiting the amount of cement in the mix. And so that's going to help make sure that the embodied carbon of concrete mixes is not going unnecessarily higher than needed to for whatever the design applications are. And that can also be implemented either on a per mix design basis, where each mix design going to be under limits, or you can look at it as a whole for a project. So if you have 3 or 4 different types of mixes that will be used on a project, and one you need to go higher strength and it's going to exceed the limits that are set there, if you go low enough on a different application and have the overall stay embodied carbon stay below that maximum, then that's a way to be flexible with it also.
I had a question about I was intrigued by the concrete recycling conversation that you were showing some information on, Alana. I mean, how widespread is that practice? Is it becoming common now that concrete is recycled, or is it landfilled in general?
I think it depends on what you're talking about. Different markets are going to have different potential for it, but in terms of using recycled concrete aggregate, it is something that is widely out there. We do a lot of it on both the East Coast and West Coast in our own operations. And it's something that's also being talked a lot about in ACI, the American Concrete Institute. There's a lot of research going on into showing what the properties of the concrete is when you use it, and trying to collect data on what is the variety of properties you get with recycled aggregate, and then how do those apply to the properties in concrete. So it is something that is pretty widespread, and there's even admixtures out there now that you can put into the back of a truck if it's still got fresh concrete, that will turn the concrete into pellets that can then be discharged and laid out on the ground. The next day you come with a loader and just break them up, and you've already got kind of a pelletized aggregate as well.
Maybe we'll do a question or two more because we're on the top of the hour here. Alex, you talked about biochar, and someone was asking, are there examples of biochar that you know of, or anyone else? Any biochar being produced and any being imagined to be used in concrete?
So it's actually, again, like I just was made aware of this, which I'm thankful for, but the way it looks like, and maybe Michael can speak more to that because I think he has it in the lab, but essentially it's already a commodity. It's typically used for soil amendment in agricultural the industry. So it's produced by the truckload, and it's available. And I think, like I said, it's in the lab right now because it does accelerate curing rates because it absorbs water. So that, again, there's 2 for 1 in those. Michael, do you have more on this?
No, we haven't tested it yet in our lab. We have done glass pozzolans and some of these other emerging technologies. But Alex, I'm waiting for you to get me a sample so I can make test cylinders. So if you give me the sample, we're going to test it.
All right.
We might have just spawned a new industry here in this webinar. So
Perfect.
Tune in next year and find out the results.
Cool.
Well, Joe, do you have any wrap-up questions for us?
I think this has been great. We'll, as always, we will circulate these amazing slideshows to everyone afterwards, so you can have a chance to do a deep dive into some of the great data sources. But we want to say thank you so much to all of our panelists. Thanks, Michael. Thanks, Alex. Thanks, Alana. Thanks, everyone, for joining us for day 4 of our Sequestration Week. Reminder, tomorrow we're closing the week with soils. It's going to be an incredible conversation. We'll send out the slides and a video recording of this webinar tomorrow morning. But thanks to you all. Have a great rest of your Thursday, and we'll see you tomorrow.
Thank you.